Hello and welcome to Romeca Corporation's three-part tutorial on how to drive a conveyor motor with a VFD. In this series, we'll discuss how to use a variable frequency drive to modify conveyor belt speeds without damaging the drive motor. You'll learn how to verify VFD conveyor drive system adequacy by checking required power versus available power and motor cooling capability, if applicable, at all relevant rates. This is part 2 of our three-part tutorial on how to drive a conveyor motor with a VFD. In this session, we will demonstrate why a knowledge of relevant powers is important. To watch any of the other videos in this series, click on the link in the upper right-hand corner of your monitor anytime during this video. Why is all of this important? This is important because we're trying to avoid what you see on the right. On the left, the picture shows a 10 horsepower Model 320 motor stator. It's designed to safely and continuously carry 12.1 amps, also called full load amps, FLA, when the motor is running at full load at its power supply frequency. Set up for 460 volt, 3-phase, 60 hertz. It should run continuously carrying the amperage which I just described. On the right, this picture clearly shows the general uniform burn of a stator which has been overstressed because required power was larger than supplied power. Here are some facts that you should know. If an AC squirrel cage induction motor is used as a conveyor drive, be aware that it is optimized to run at a certain power supply and carry a certain full load amp rating. That will be on the data plate, FLA. It has no inherent ability to protect itself from current overload, and that's why external overcurrent protection is necessary when using three-phase motors, not only on conveyors, but in any instance. Current overload damage may occur when required belt pull exceeds available belt pull, or when required power exceeds available power, and of course when external overcurrent protection is not working. The system will self-destruct. Current flow is proportional to the power required from the motor. Regardless of what it's designed to provide, current flow is proportional to the power required from the motor. If it's overloaded, then heat from excess current can burn the motor, generally in the stator. If the motor cooling system cannot dissipate stator heat, that also can cause the motor to burn. So in summary, inadequate power implies too much current in the stator, which implies too much heat, which implies motor failure. Likewise, inadequate cooling would imply too much heat, and that implies motor failure. Both of these things need to be avoided. Now let's discuss relevant powers and heat dissipation. Power is the rate of doing work, or the amount of energy transferred per unit time. Electric power is converted into mechanical power when an electric motor is used to drive a conveyor belt, and heat is a natural byproduct. Required mechanical power is generally calculated in foot-pounds per minute and expressed as so many horsepower. A standard electric power supply is defined as the supply which is readily available and installed to power the drive system. The installed electric motor power, expressed in horsepower, is what is chosen to drive the conveyor belt. Available electric power supply may be constant if 460 volt 3-phase 60 hertz is used as supplied by the power company or by the generators on site, or it may be various. If a variety of frequencies are going to be used with a VFD, then available electrical power supply will vary. Likewise, available electric motor power, is that constant or is it going to vary with various hertz? Heat. Motor stator heat must be continuously dissipated while the drive provides continuous full load mechanical power. Required steady-state cooling may use airflow, as in the example of a TEFC motor, which is typical in an exposed drive system, totally enclosed fan-cooled motor, very common, or required steady-state cooling may use oil flow, and as in the case of a Romeca motorized pulley. We'll see examples of an exposed drive system and an internally powered drive system in the coming slides. We need to verify that the steady-state cooling necessary is available. Does the rotor RPM provide enough cooling, or is it too slow or too fast, and thereby compromising the cooling system? Work may be defined when a constant force of magnitude F exerts itself on a point which moves a displacement of S. Work equals force times displacement, or W equals Fs. Now, in imperial units, work is expressed in foot-pounds. And if our force is 1,000 pounds, and if the point moves in a straight line, a distance of 330 feet, then the work done is 1,000 pounds times 330 feet, or 330,000 foot-pounds. Now let's define mechanical power. Power is simply the rate of doing work, or so much work per time. Mathematically, it would be expressed as follows: force times displacement divided by time, or the equation Fs divided by T. Alternatively, we can say the same thing in a different manner. Power equals force times velocity, or force times S divided by T. Our example, once again, a force of 1,000 pounds exerting itself on a straight line for a displacement of S. If that takes 1 minute, then the required power will be, as you can see here, Fs divided by T, 1,000 pounds times 330 feet divided by 1 minute. Alternatively, we can say it's a force of 1,000 pounds multiplied by 330 feet per minute. Both equations give the same result, 330,000 foot-pounds per minute. Since 1 horsepower equals 33,000 foot-pounds per minute, we know that required power to do the work is 10 horsepower. Now, Romeca Corporation has made numerous videos available, both on our Romeca Corporation YouTube channel and the Romeca Corporation website. We also have free software available to assist conveyor designers and operators to calculate required power, whether it be for unit handling or for bulk handling. And let's look at an example of a slider bed conveyor, which is horizontal, moving 50-pound boxes at 50 feet per minute. Required power equals force times velocity. If we know that the belt speed needs to be 50 feet per minute, 140 pounds times 50 pounds gives us 7,000 foot-pounds per minute. Dividing by 33,000, our answer comes out to be a required power of 0.2 horsepower. Now the designer can select an electric motor to provide enough mechanical power. In bulk handling, we calculate TE, effective tension, and we need to determine the tension required to overcome friction, gravity, and momentum. As previously, we know that required power equals force times velocity, or required power equals belt pull times belt speed. Our methodology is the semi-historical method, and you can see the equation here. And we know that required power equals TE times V, or belt pull times belt speed. Say we're going to move a certain quantity of stone at 330 feet per minute, and our calculations tell us that the belt pull, or the effective tension, is 1,000 pounds. 1,000 pounds times the selected belt speed of 330 feet per minute gives us a required power of 330,000 foot-pounds per minute. Divide by 33,000, we can see that the required power to do what I just described is 10 horsepower. And now we can select an electric motor to provide enough mechanical power at whatever power supply we choose. Now let's look more carefully at AC motor rotor revolutions per minute, or RPM. First, we define 1 cycle. 1 hertz is the dimension that we use to describe 1 cycle. When an alternating current goes from neutral to positive, back to neutral, to negative, and back to neutral. 1 hertz is defined as 1 cycle. 1 cycle per second is 1 hertz. The typical U.S. power supply is 60 hertz. This is the way it's generated by the power plants. And so that means in 1 second, we will see 60 cycles. A 60 hertz power supply has 60 cycles of alternating current per second. Now let's look more carefully at an AC squirrel cage induction motor designed to run on 460 volt 3-phase 60 hertz. We have the stator, which is the stationary part, and we have the rotor, which rotates. Indicated with the positive and negative symbols, you can see that we're trying to depict a 2-pole motor. So we have 2 poles in the stator, we have 2 poles in the rotor. As current flows at 60 hertz through the stator, at 60 cycles per second, a magnetic flux forces the rotor to turn at 1 revolution per cycle. So the flux field in the stator is causing the rotor to rotate. And since at 60 hertz the rotor rotates at 60 revolutions per second, the motor RPM is simply the product of these 2 numbers. 60 times 60 is 3,600 RPM. As I mentioned previously, we're going to ignore motor slip, which is a phenomenon that occurs when an asynchronous motor provides full load. To make the math easy, we're just going to use synchronous speeds. Let's see what happens when we change the power supply frequency. If we reduce the frequency from 60 hertz to 30 hertz using a VFD, now as 30 hertz current flows through the stator and the magnetic flux forces the rotor to turn at 1 revolution per cycle, the rotor is only rotating at 30 revolutions per second. Therefore, the RPM becomes a product of these numbers, 30 times 60, or 1,800 RPM. Cutting the frequency in half cuts the rotor RPM in half. Now let's have a look at a 4-pole motor running on a 60 hertz power supply. A 4-pole motor is different from a 2-pole motor, and you can see the symbols here. We have 4 poles in the stator, we have 4 poles indicated in the rotor. In the case of a 4-pole, the magnetic flux is going to force the rotor to turn a half of a revolution per cycle. That means at 60 hertz, the rotor rotates at 30 revolutions per second. So the RPM is 30 times 60, or 1,800 RPM. Let's have a look at an 8-pole motor. In an 8-pole motor, you can see it symbolized here. The magnetic flux is going to force the rotor to turn 1/4 of a revolution per cycle. And so therefore at 60 hertz, the rotor rotates 15 revolutions per second, and the RPM becomes the product of 15 and 60, or 900 RPM. Now let's look at a real-world case. Let's say that we've calculated the mechanical power required at this pulley, and we want a belt speed of 330 feet per minute. We can install a TEFC motor. Let's say we're going to install 10 horse of electric power. Note that this exposed drive has cooling fins and a shroud enclosing the cooling fan. If we know that the pulley has a radius of 0.5 feet, the circumference equals 2 pi r, or 3.1416, it's easy to calculate the pulley RPM simply by dividing the belt speed by the circumference. That gives us a pulley RPM of 105.04. If we decide to install a 2-pole motor at 460 volt 3-phase 60 hertz, we know from what was just displayed earlier, the motor RPM is 3,600 RPM. So to calculate the speed reduction required in this example is nothing more than dividing 3,600 by 105.05, or we need a reduction of 34.3 to 1. Let's alternatively compare a motorized pulley drive system. Here we have an oil-cooled AC squirrel cage induction motor, but the components are virtually identical. We have a pulley shell, so let's say it's the same diameter. We have an AC squirrel cage induction motor, say it's 2-pole. We have a gearbox providing whatever ratio is needed. And very importantly, we have a certain quantity of oil to provide lubrication of all the mechanical parts and to provide the all-important cooling of the stator in steady state. So let's say we require 10 horsepower of mechanical power at the face of the pulley, and we're going to install an electric motor of 10 horse. If the diameter is identical to what we described previously, the RPM is the same. If we select a two-pole motor, as we did previously, the RPM is the same. Therefore, the speed reduction, as in the previous example, would be 3,600 divided by 105.04, or a speed reduction of 34.3 to 1. Now let's try to understand the relationship between required power, which is calculated as force times velocity, and installed power, which is calculated as torque times angular velocity. As I said previously, if force equals F and velocity equals belt speed, required power is simply force times belt speed. And in the example we presented previously, we calculated a mechanical requirement of 10 horsepower. Since the drive system is going to be providing power by spinning, it's important to know that torque equals force times radius, or F times the radius R. Angular velocity is defined as revolutions per minute times radians per revolution, or RPM times 2 pi. If we know we intend to install power at the pulley of 10 horsepower, we can calculate the torque at the pulley face as follows. We know that 10 horsepower has been installed. That's 330,000 foot-pounds per minute. We simply divide by the product of these two numbers, 105.04 times 2 pi, and the answer is 500 foot-pounds of torque. As a quick check to make sure this makes sense, since we know that torque equals force times radius, and we know the radius is 0.5 feet, 500 foot-pounds divided by 0.5 feet tells us that we have a belt pull of 1,000 pounds. 1,000 pounds of belt pull is provided, 1,000 pounds of belt pull is needed. Let's have a look at a motorized pulley. If required power at the pulley face is 10 horsepower, and installed power is a 10 horse, pulley torque is 500 foot-pounds, and belt pull is 1,000 pounds. Let's see what is installed by having a look at the two-pole motor shaft. 10 horsepower at 3,600 RPM at 60 hertz tells us that the installed power at the rotor is FR times RPM times 2 pi. We divide 330,000 foot-pounds per minute by the product of 3,600 RPM and 2 pi, and that tells us that the motor torque is 14.59 pounds. So 14.59 foot-pounds of torque at the motor gives us 500 foot-pounds of torque at the pulley face. We said that we need a gear reduction of 34.3 to 1. If we multiply the motor torque of 14.59 by that gear reduction ratio, the answer, as you can see, is 500 foot-pounds. It's essential that each conveyor drive system is selected correctly. A motor reducer combination which was optimized to yield 500 foot-pounds at 105 RPM might not be appropriate if the belt speed is increased or decreased significantly. Have you installed a race car but now need a truck, or vice versa? Your drive system manufacturer can help with that decision. For example, Romeca motorized pulleys are available with motors of 2-pole, 4-pole, 6-pole, 8-pole, and 12-pole. And we have pulley speeds from 7 RPM to as high as 452 RPM. Our staff can help you select a new drive system if the speed change you're considering makes the existing drive system inadequate. That concludes part 2 of how to drive a conveyor motor with a VFD. We learned why a knowledge of relevant powers is important. We hope you found this short tutorial useful. To watch any of the other videos in this series, click one of the links at the bottom of your monitor. To go to our website, click the link in the upper right-hand corner of your monitor now. Thanks for watching.